Okay, let's get to work. Now starting chapter 5. Probability distributions. I hope I can make it all the way to 5.5 with Poisson, but that's an optional one. If we get there, great. If we don't, that's okay. And this is a pretty quick turnaround. Your next test is only a couple weeks away. But before we just dive into things here, a pause to reflect of where we've been so far and how does this fit in the overall sequence. Because believe it or not, there is a method to the way the material is put together, and I think the author has it laid out very rationally. In the first 3 chapters, we talked about descriptive statistics. And you can think of it as they're almost post-mortems. The data's been measured, it's collected, I got a great big pile of it. How can I use graphs, charts, pictures, and statistics to describe what this means? But it's kind of a historical look at it, isn't it? The data's there. Well, chapter 4, we studied the concept of probability and how to calculate it in a lot of different ways. And generally, when you're using probability, you want to make a prediction about the future. How likely is something going to happen? It happen. Or in a slight twist of that, you might say, well, here's an outcome I observed. Is that a very likely outcome? Those questions are going to be really important, particularly in 5 and 6 and all through your career in 106, where we go into inferential statistics. And in inferential statistics, we really do the powerful, really important application of statistics that's out there in the real world all the time. When companies like Pfizer's do drug studies to see if a new medication actually works, what they're doing is inferential statistics. And they're looking at their data from their experiment and saying, how likely is this result to have occurred if my medication didn't work, or if it did work? So this concept that we're introducing now, probability distributions, calculating probabilities, and seeing what's likely and what is unlikely, what's usual or what's unusual, is core to the mainstream of statistics, used out there in industry and real world all the time. As always, when we start a chapter, we've got lots of definitions and concepts to introduce. So that's going to be what it is mostly today. More terms. Start with big 2 are random variables and probability distributions. And we're talking about two varieties of random variables, discrete and continuous. Then after we introduce that, we're going to focus in chapter 5 on just discrete random variables. In chapter 6, we'll pick up continuous again, and then for the rest of your career, 105, 106, you'll be using continuous random variables. Okay, so what is this thing called a random variable? Well, often in mathematics, mathematicians don't like randomness, do we? We like things in all its gory detail. And we write expressions like y is equal to f of x equals x squared plus 10, and it's very deterministic. You give me an x, I'll tell you exactly what y is going to be. No questions asked. Let's go on to the next one. All right? It's very convenient to have these kinds of expressions, these functions, because we can do so much with them. What we're doing in chapter 5 with this concept of a random variable and probability distribution is we're trying to move away from the kind of techniques we used in 4 to something that's a little bit more like good old mathematics, but not quite, because here's the big difference. Where x here is a given, x now, the random variable, I can't tell you what it's going to be. I can tell you its permissible values. I can tell you what probability is that it will have, that it will take on a particular value. but I can't tell you in advance of my experiment or my procedure what the value is going to be. And that's the main idea, and a huge difference from what we're used to doing in math to what we're doing now in probability distributions and random variables. So the key requirements of a random variable, there's two things. We're always going to be talking about numerical values, no exceptions. Up to now, in probability, we could go numerical values, we made lists of letters, we did things in a lot of different ways. From here on out, a random variable is always a numerical value, and it's determined by chance. That's all that's required. And a lot of the experiments or procedures we've talked about so far can easily be turned into a random variable. You're just looking at it in a slightly different way. Rolling dice. We've done lots of examples calculating probability with dice. We made tables of outcomes or lists of possible outcomes to calculate probabilities. Well, here's how we're going to look at it now. We'll still have this procedure. I roll the pair of dice twice. My random variable has to be numerical value. It's going to be the total number of dots I saw on those two dice. That's going to be anything from 2 to 12. I can't tell you in advance what number it will be. I can tell you it's between 2 and 12, and we can calculate probabilities that it will be one of those values. But I can't tell you what value it will be. Tossing a coin. We've done this a lot, haven't we? And often we did little strings of H's and T's. It said, oh, that represents 3 tosses, a head, a tail, and a head. All right, we're going to move away from this kind of representation of the problem to that of a random variable, where I don't want to list out strings of possibilities. I want to use a numerical value to represent my outcome. So here I'd say, toss the coin 3 times. That's my procedure. My random variable is the number of heads. Number of heads and 3 tosses. 0, 1, 2, or 3. Think of Mendel, the genetics experiment. Plant pea seeds. Plant 100 of them. See how many have, what was he looking at? Wrinkled skin versus yellow pods versus all of that. Perfect example of a random variable. I don't know what it's going to be in advance, but I can tell you the permitted values. The last 3 are a little bit different in the sense that they are measurements. The first 3 are counts, the second 3 are measurements. My procedure could be select one of you at random and measure your height. I don't know that value, that height in advance. That's my random variable. I know the range of it, but I can't say precisely which value is going to occur. Temperature, we can talk about going to the steps of Mallory Hall and looking at the temperature at noon. Examples of random variables. And this chart makes it clear how we've shifted from chapter 4 of the probability to now how we're looking at the same procedure. When we looked at this procedure, flip a coin 3 times. And remember how we list all the possible outcomes, all the H's and T's, and then calculate probabilities using those sets? All right, now we're going to step back a bit and say, well, you know what? I'm interested in just the number of heads. I don't care about what order they came in. X is my random variable, the number of heads in 3 tosses, and it can be 0 through 3. And those numerical values are going to be useful now because I can do things with those and calculate statistics that I can't if I just had a string of 3 letters. And it's pretty obvious now that I can do some calculations in this example with probabilities. The probability that X is 0, that's no heads and 3 tosses. That's just 1 out of 8. Probability that it's equal to 2, well, it's 3 out of 8. We calculated those probabilities before, didn't we, in chapter 4? But we just didn't express it as a random variable. We just said the probability of 3 heads or 2 heads is 3/8. Same idea, just looking at it a little bit differently. Okay, now let's pause and before we go further, talk about the difference between discrete and continuous random variables. In Chapter 1, we were just beginning to think about collecting and studying data. We made a distinction between discrete and continuous. Remember back then, discrete, usually a finite number of values. Doesn't have to be, but almost always finite. Often it's a count of something, so it's integer. Often, doesn't have to be. But the hallmark of discrete random variables are their gaps. It's not a continuous scale. So if the random variable is the number of emails you receive in a day, it's a count of something. That can be a really large number. You can get 100 emails, you get 102, but you can't get 100.5. That's discrete random variable. Continuous, but it's always an infinite number of values. You can't have a continuous random variable unless it has an uncountably infinite number of values. Think of a continuous scale. If I had a ruler up here, and I could with infinite precision pick out any little spot on that ruler. And between any two spots, there's always another one, isn't there? There are no gaps. That's what we mean by continuous and no gaps. There's always between, no matter how close you are together, your two values, there's always more in between. Whereas discrete are typically counts, these are typically measurements of real world things like height and weight and distance and speed and so on. Now let's go back and look at these previous examples really quickly and categorize them. The experiment with the dice, the coin toss, and genetics, they're all discrete because they're counts of things, aren't they? Counts of heads, counts the number of spots on the dice, counts the number of plants with yellow pods, discrete. The coin weight, the height of a cadet, temperature, all those are continuous. Because if you need just one little break here, you can assume infinite precision in measurement. I know that's not really possible. There's always, between any two heights, there's always another height that's possible. So those are examples of continuous. And now that we've defined those, we're just going to focus on discrete. Okay, briefly here, a little bit of a side. I said that discrete random variables almost always have a finite number of values. They don't have to, though. They can have a countable number of values, an infinite, but it has to be countable. What's that? Infinite but countable? I only put this in here. If we get to the Poisson distribution, it will be an example of a discrete distribution that has a countably infinite number of values. And in that case, countable means that I can take each of those values and put them in correspondence with the integers. I can count them, 1, 2, 3, so on. There might not be any upper bound maximum, but I could, in theory, just keep counting and counting and assigning an integer to it. So as an example, if I could measure the number of photons passing through Mallory Hall at any second, that's a big number, but it's a countable number. It might not have any upper bound. It would get really large, but it's countable, so it's discrete. I have 100,000 photons in that second. I can have 100,001. I can't have anything in between. All right? Got that idea? Don't worry if it's not real crystal clear. If we get to Poisson distributions, then we'll talk more about that. All right, now the second key concept, probability distributions. We talked about random variables. The way we study random variables is by looking at their probability distribution. And for discrete random variables, we use tables and histograms primarily. Continuous random variables, we use functions and graphs. So in Chapter 6, we'll be doing using these techniques. Chapter 5, tables and histograms. But in either case, there are two requirements for a a distribution to be a probability distribution. That is that the P of x, probability of that value of a random variable, always has to be between 0 and 1, inclusive. That makes sense, doesn't it? I can't have a probability less than 0 or greater than 1. Then the other requirement is that if I take the probabilities of each of my permitted values to random variables, and I add them all together, it has to equal 1. Because that's all the possible outcomes there are, right? There isn't anything else. So all those probabilities would have to add to 1. Let's go back to the coin example again. I'm counting the number of heads in 3 tosses. X is my random variable. It could be 0, 1, 2, or 3. And it can't be anything else. So the probability of it being 0 plus the probability of it being 1 or 3 or 2, if I add those up, it has to be 1. Because that's all there is. And that's the rationale for that second requirement of the probability distribution. Add everything up, you get 1. Now these tables are convenient ways to work with discrete probability distributions. So let's just practice a few calculations with it. It's pretty natural. If you are asked to find the probability that x is between 1 and 2 inclusive, right, that was the probability statement. How would you calculate that? Well, you go to the table and you find 2 entries, 1 and 2. Now add those together and I get 6/8. Now I make an assumption here. Anybody catch me on this? This is really equivalent to saying x is equal to 1 or x is equal to 2. Does that sound familiar? That or? In chapter 4, what rule did we use when we calculated probabilities that had or? The addition rule. And what is the addition rule?
P of A plus P of B minus the probability of A and B.
What's the probability of A or B? Well, wait, how did I get away with this, not putting in this term then? I just added those 2 together. I didn't subtract anything out. Is there a mistake on my slide? Not this time.
Is it because it has to equal 1?
Not exactly.
You're saying that they're not overlapping.
Okay, what's a more statistical term for not overlapping? It starts with dis.
Disjoint.
Disjoint or mutually exclusive. That's one of the nice properties of these discrete random variables in the table here. Each of those outcomes are mutually exclusive or disjoint, right? They have to be. Think of the procedure. I'm flipping a coin and counting the number of heads. And that number of heads is my value of the random variable. Is it possible to flip a coin 3 times and get 2 heads and 3 heads? No, I can't. If I get 3 heads, I've got 3 heads. I can't have 2 heads at the same time. I either had 2 heads or had 3 or had 1 or 0. They're disjoint or mutually exclusive, so I'm justified in just adding those 2 numbers together. And there's another example using the or, writing it a little bit different. Probability x equals 0 or x equals 2. Because of this property, I could just add those together right out of my probability distribution. There's a couple other possibilities. We might say, what's the probability if x is at least or less than 2, or at most 1, or x is less than 2? We're going to have different ways of stating the same probability question. And you need to be comfortable moving back and forth from the English, x is less than 2, to the mathematical statement, and then using the table to find that probability. That one is pretty straightforward. It's less than. What about something x is at most? If I say at most, what does that mean? Well, it could be 2, right? If it's at most 2, it could be 2, it could be 1, or it could be 0. So at most would be less than or equal to 2. Be able to make that translation. At most, less than or equal to. At least. Well, at least would be greater than or equal to. And then I can easily go to the table here. Oh, greater than or equal to 2. That's those 2 rows. Add up the probabilities, and I've got the answer. All right, let's pause here for a little reflection. And I'll let the first row have the honors today. Which of the, are these probability distributions or not? You got keys. Example 1. Is that a probability distribution? No, because
I'm not really sure.
all right. What are the 2 requirements? Just 2 things have to be true for it to be a probability distribution. What's the first one, the easier one? All right, that's actually the second one I was thinking of. All the probabilities had to add to 1. And Vosburgh.
That was mine.
That was yours too? All the probabilities have to be between 0 and 1. Did all those probabilities, did they add up to 1? No, a little bit short. It was 0.95. He's right. That's not a probability distribution. Okay? Number 2. Okay, Russell. Sound real certain there.
Well, the one on the left, isn't that directly discrete?
Okay, what about the ones on the left? What are those things on the left column there? We have a name for them. They are they're the values of a random variable. And you're troubled by the negatives and the decimals? Did we say anything about what the value, the random variable itself had to be? Did we make any restrictions on it? We didn't. So it's perfectly legitimate to have negative numbers here. I could have pi, I could have the square root of 17 as an x. That's no problem. That's fine.
Well, the right side adds up to 1, so.
Yeah. And I did this deliberately. This is to get you to think about what's important here. The left column really isn't important. That's the value of the random variable. It's these probabilities we're focused on. They all have to be between 0 and 1, and they have to add up to be 1. We'll get number 3, please.
Yes.
Because?
All the variables on the right side add up to 1.
And they're all between 0 and 1. All right, right, see? Number 4. Because?
The numerical values only come out to 0.99.
Yeah, this is a bit of a gotcha. In those cases, there's going to be a lot of times we're working with probabilities and we get fractions like a third, 0.33333, and they never going to add up to 1 precisely. We'll have to round at some point. 0.9999, that's good enough. 0.95 is not. We saw that in the early example. Okay, another way we can express probability distributions is with a probability histogram. In this case, on the x-axis, these are values of the random variable. So I'm saying my x can be 0 through 12. In this case, the random variable. I have my bars, and the height of the bar is the probability. The probability that x is equal to 12 is, maybe 0.08, something like that. it's a nice graphical representation of the probability distribution. And human beings are pretty good at looking at graphical information and understanding what it means. For example, just looking at that, if you perform this procedure and you got the value of the random variable equal to 3, would you be surprised? That Faust, would you be surprised?
Yes.
Why?
Because there's no trigger.
Yeah, it almost looks like there's no probability, or else it's really, really small. What values would you expect to get if you do this procedure? What range of values would you see most often? Good.
The most you see 10.
10, 9 through 11. Certainly you wouldn't see anything other than a 7 through 12 very often, would you? In fact, I'm kind of leading to something we'll talk about later. These values, 4, the 5, and maybe the 6, would be called unusual values. And it's going to be important later on to understand when I perform a procedure and I get a value, I need to know, is this kind of reasonable? Does this happen a lot, or is it unusual? And how unusual is it? Because I'll be making my decisions and my inferences based on that. Okay, finally some math formulas. This is a math class. These should look familiar to you. They're on your formula sheet, so I'm not worried about you memorizing them. For the most part, we'll be using a calculator to compute them. But let's go through them. That first symbol, what's that called? U. And U is what?
The average?
It's a mean.
Oh, it's a mean.
It's a population mean. Or mean. And the formula is sigma x p of x. Let's just look at this a little bit. What's that Greek letter, capital sigma, mean?
Add these up.
Yeah, add this stuff up. What am I adding up? Well, x is my random variable, and I'm multiplying it times the probability that I would get that value of the random variable. And I'm calling that my mean, or also the expectation. For our purposes, the expected value and the mean are synonyms. And it's really just a matter of perspective or problem, but you calculate them the same way. Then we have sigma, the standard deviation, and sigma squared. That's the formula. And I'm going to show you how to calculate these using the calculator next step. I'll just give you a heads up on StatLab. When you're working some of these problems, if you ask for help, the author doesn't know you have your TI calculator, so he's going to try to be helpful and show you these formulas and all sorts of shortcuts as if you were adding them all up by hand. That won't be very useful to you. Okay. How to get some exercise. Fire up those calculators. Those batteries. I want you to put L1 the x's and L2 the p of x's. That's a probability distribution, discrete probability distribution. You can verify that the sum of all the p of x's is equal to 1. And we're going to calculate the mean, standard deviation, and the variance of that probability distribution. When you finish putting those in, give me a thumbs up so I know when to proceed. Okay, one thumb up. You should be fast at this. It's just like texting, right? I know you're all very good at texting.
You're supposed to go south, right?
Yes, L1 and L2. Okay, anybody need more time? Going once, twice? Okay, that is our discrete probability distribution. To calculate the mean and standard deviation, we're going to use our old friend 1-var stats. So it's stat calc on your calculator. Then the very first option is 1-var stats. Stat calc.
Can you just press that?
Just press 1-var stats, and then depending on your calculator, you might be at the prompt line and it's waiting for you, or you might be displayed, it might ask you for list, then it says freak list, and then something else. Different TI calculators versions have different responses there. You want to put in L1 and L2 as the first and second list.
How do you do that?
What do you have for your,
It just says one more stats.
you put in L1, comma, L2.
Where do I find that?
You do have this second, and then look for L1. Yeah? Are we all on board here? Russian?
So you said one, L1 for the list and L2 for the frequent?
Yeah. And when you've done that, then the output of 1-var stats, X bar will be the mean. The TI calls X bar is the mean. And what S of X is the standard deviation. And those are the answers you should get. 5 and 1.584. And if I wanted to know the variance of that distribution, what would I do? How would I get the variance of that distribution? What is the variance? Squared. The variance is sigma squared. The standard deviation is the square of the variance, square root of the variance. Your TI calculator doesn't give you sigma squared, but it gives you sigma. So just take it and square it if you need the variance. Good to go. And the expected values, I said, we're going to treat it as a synonym for the mean. There'll be some problems where you're asked, find the expected value, same as finding the mean. All right, that's where I'm going to break for today. Just one comment here. I think I mentioned this before. To the extent you can, try to stay in your seats during the lecture. We are trying to have a film in here. If things are urgent, take care of them. If you can, take care of things before class. It sounds like there's a various plague moving around here that's making it more challenging. I understand.